Welcome. In this video, we're going to look at the consequences of the derivative of the exponential function to be able to help us find three additional formulas. First, we're going to look at how we can use the derivative of the natural exponential to find the derivative of an exponential with a different base. So for example, 2 to the x or 3 to the x. Second, we're going to look at how we can use the derivative of the exponential to find the derivative of the logarithm. The main one will be the derivative of the natural logarithm, that's base e, but we'll also look at other bases. And finally, the exponential gives us a way to prove the power rule for any power p. Previously, we've only looked at powers that are integers, and this will give us a way of proving the derivative rule for any other power. All right, so let us revisit the derivative of b to the x. For any base b, it has to be positive. And the way we'll do that is we will rewrite b to the x in terms of the base e. So let's start by defining our function. The idea behind rewriting our function in base e is we can rewrite this in a way where we'll know how to find its derivative. So remember that exponentials and logarithms are inverse functions. So we could rewrite f of x as the composition of an exponential and logarithm. Because they're inverses, we can compose them without any change in our function. And if I thought about what that meant, I can rewrite it in terms of base e. Once I've rewritten the function, I can use the properties of logarithms. Logarithms have a power rule that this power will be able to be rewritten so that now I have e to the x times a number where that number is the logarithm of b. Now we're ready to find the derivative. The derivative of our function, f prime of x, is what we get when we take a derivative, so that's the derivative operator, on our function. And we're going to use the rewritten version. So we can write that as e to the x times the natural log of b. And this is a chain rule problem. My inside function, the exponent, is x times the natural log of b. And the outside function is e to the u. So that when I calculate my derivative, I get the derivative of the inside, that's e to the u, because exponentials, base e, don't change. So I get e to the u times the derivative of u. And this is just x times a number. The derivative of x times a number is the number. So now I found my derivative. All that's left is I'm going to go back and use the original expression for f of x, because I've got f of x could be written as e to the x ln b, or the original form b to the x. And so we've found it. We found the derivative of b to the x. The derivative is b to the x times the natural logarithm of the base. So some quick examples. If I took a derivative of 2 to the x, the derivative rule says it's the same exponential, 2 to the x, times the natural log of the base. If I did a chain rule, if I wanted the derivative of let's do 3 to the x squared, I have a chain. The inside function is x squared. The outside function is 3 to the u. And so the derivative of 3 to the u is 3 to the u times the derivative of the base. And then the chain rule, I multiply by the derivative of the inside function, 2x. Our second function that's a consequence of the derivative of the exponential is it allows us to find the derivative of the inverse, the logarithm. So we know that the exponential and the logarithm are inverses, and that allows me, if I have a positive value x, that I can write x as e to the natural log of x. We're going to use the principle that if I have two different ways of finding a derivative of the same function, they must give the same value. So if I find the derivative of x the normal way, I just get that the derivative of x is 1. On the other hand, if I take the derivative of my new formula, I have an expression of the form e to the u. And so we know from the chain rule that the derivative of e to the u is e to the u, so that's e to the natural log of x, times the derivative of the u. which is the logarithm's derivative, which we don't know yet. So e to the ln of x is really just x, and so I get that the derivative of my function is x times the natural log's derivative. Once I have two different ways of finding the same derivative, I can set them equal and solve for the unknown. I know that the derivative of x is 1, but it's also x times the natural logarithm's derivative. So if I solve for the natural logarithm's derivative, I get the natural log's derivative must be 1 over x, and this is for x greater than 0. All right, the logarithm is not defined for negative values of x, and so I can't talk about the derivative of the logarithm when x is less than 0. But I can talk about what happens if I take the logarithm of an absolute value. So what I want to do is I want to go back and think about if x is negative, I could think about x as being the opposite of its absolute value. So I can rewrite x as the negative exponential of the logarithm of the absolute value of x. Now we can do the same thing. If I take the derivative of x, I get 1. And if I take the derivative of the new formula, then I get an exponential. I get negative e to the same u times the derivative of the u. Now, negative e to the natural log of the absolute value, that's just x. So I get an equation 1 equals x times the derivative of the natural log of the absolute value of x. So I can solve for the derivative, and what I've found is a new formula. When x is negative, I've learned that the derivative of the natural log of the absolute value of x is also 1 over x. Now I want to ask a question for you to think about. Why couldn't I just write, when I did this step in the chain rule, why didn't I write the natural log prime of the absolute value of x? Think about that. And how does the notation relate to what I did write? All right, what we found is that if I take the derivative of the logarithm, I get 1 over x. And if I take the derivative of the logarithm of absolute value of x when x is less than 0, I also get 1 over x. And so this equation, the derivative of the logarithm with an absolute value, will be equal to 1 over x for all x's except 0. For our last consequence of the exponential's derivative, we'll revisit the power rule. Now, when we first found the power rule, we did it for a few examples using the definition of the derivative. Then we were able to use the product rule and induction to show that the power rule worked for any positive integer, and we could use the quotient rule to show that it worked for any negative integer. Now that we know the derivatives of exponentials and logarithms, we can show that the power rule works for any number p. All right, so the argument is the same as what we just did for the logarithm, except now we're going to rewrite x to the p. All right, we have two different ways of writing x to the p, so we can say that if I want to find the derivative of x to the p, it's the same as if we took a derivative of e to the power p times the natural log of x. Now this is an e to the u form, and so the general exponential's derivative is, I get e to the same power, e to the u, times the derivative of p ln x. And now I can rewrite. This exponential is just a different way of writing x to the p. P is a constant, so it's a constant multiple, and the logarithm's derivative is 1 over x. And so when I simplify this, I have a constant p, and then x to the p times 1 over x, that's where subtracting 1 power comes from. So this argument worked for positive x's, and if I want to deal with negative x's, I have to think about the absolute value. For negative x's, x to the p might be positive or negative. It depends on the power p, whether it's an even or odd power. For certain fractions, x to the p is not even defined for negative x. But when it is defined, x to the p can be written as some constant, which represents the sign, plus or minus 1, times e to the power p of the natural log of the absolute value. So when it's defined, this allows me to write that the derivative of x to the p is the same as finding the derivative of whatever this constant is times the exponential that we're looking at. Well, the constant multiple stays. The derivative of an exponential is itself times the derivative of what's in the exponent. So that's p, and we just learned the logarithm's absolute value, even with an absolute value, is 1 over x. The sigma e to the p ln x, that's just a really funny way of writing x to the p times p times 1 over x, and notice we're back where we wanted to be. I get p times x to the p minus 1. So the simple argument when x is positive was fairly straightforward. When x was negative, we had to worry a little bit with absolute values, but either way, I get the power rule is valid. In summary, what have we found? We found that when I take a derivative of b to the x, I get the same function times the logarithm of the base. And when the base is e, because the logarithm of e is 1, I get back e to the x. Next, we found that when I take a derivative of the natural logarithm, I get 1 over x. We learned this generalized a little bit further, that I could take the absolute value of x and put it in the logarithm, and I get the same derivative. Now, if you use the same idea that we used for exponentials and logarithms base e, and you did the same thing to base b exponentials, arbitrary, what you would find is that if I take a derivative of a logarithm in another base, say base b, you again get 1 over x, except that you need to multiply by 1 over the natural log of the base. In some sense, you want to think of this as being the inverse idea of the natural log of b being multiplied when I do the exponential. It's a challenge question. See if you can find out why that's true. And then finally, we found that I could redo the power rule for any power if I thought about x to the p as a composition with the exponential. Now, making this change of representation using the exponential actually can allow me to do lots of different derivatives where there's a power involved, where it's not a simple exponential, nor is it a power function. So if I convert it to this base e exponential, then I can use the rules of differentiation to find my answer. All right, I think the exponential is an amazing function, and it allows us to do an awful lot. And I hope you were able to learn something from this video. Thanks for watching.